We are now going to move on to non-parametric tests. These are tests where we're not going to estimate a parameter like the mean or the variance. So the first one that we're going to look at is called a chi-square goodness of fit test. So we'll start with an example. Historically, the proportions of blood types A, B, AB, and O in the United States have been 0.41, 0.1, 0.04, and 0.45 respectively. A random sample of 200 Americans was selected, and the blood types were, there were 89 A's, 18 B's, 12 AB's, and 81 O's. Is there sufficient evidence at the 5% significance level to claim that current proportions differ from historic values? Now, we've looked at population proportions before, but we've always looked at a single proportion or the difference between two proportions. Here we have four proportions that we would be looking at. So instead, we're going to note that this problem has a single categorical variable. And that category is blood type. So we have one variable, blood type, and it has four categories, A, B, AB, and O. Now, our hypotheses for this test are going to be the null hypothesis. That's where nothing interesting happens. So the null hypothesis for this test is going to be that the probability of being type A is still just 41%. The probability of being type B is still 10%. The probability of being type AB is still 4%. And the probability of being type O is 0.45 or 45%. Now, the alternative hypothesis that we're going to consider is at least one of these proportions, or probabilities if you like, is different than the historical value. So our goal is going to be to find a measure of the sample data that quantifies the strength of evidence against the null hypothesis. So we're going to consider what's called a chi-square goodness of fit test. That test was first proposed by a British statistician, Carl Pearson, back in 1900. And in order to test our hypotheses, we're going to calculate the distance of each observed frequency, which we will call O sub I, from the expected frequency, which we will call E sub I. So O sub I, that's going to be how many people we observed with type A blood or type B blood, etc. So we're going to look at the sum from I equals 1 to K, where K is the number of categories. We are going to take the observed frequency, subtract the expected frequency, square that, and then divide by the expected frequency. Here, K is going to be the number of categories, and the expected frequency is going to be the total number of observations, N, times the probability of the category I. So, for example, the expected type A blood would be, so E for type A blood is going to be 0.41, because that's what we would expect, times 200. Okay. Now, what can we learn from this test statistic? Well, let's make some observations. If chi-squared is small, that would mean that the O sub i's are close to the E sub i's, which suggests that the data agree with the null hypothesis. We're not going to accept the null hypothesis, but if the O sub i's are close with the E sub i's, that would say that it's more likely that the null hypothesis is true. But if the O sub i's are far from the E sub i's, then that's going to give us a large chi-square statistic, and that suggests that the data disagree with the null hypothesis. So essentially, if chi-squared is large, then we're going to be able to reject the null hypothesis. Now, our key assumption is that we're going to assume that the population has a multinomial distribution. So you can remember this back from Math 350. So that means that the outcome of each trial falls into one of k distinct categories. In this case, A, B, AB, or O. And the outcome of each trial is independent of other trials. So in this case, we're going to randomly select a person and then test to see what blood type they have. Then we'll randomly select another person independently and test to see what blood type they have. Okay, we're not going to include people in the sample who are family members or something that would make it so that each person is not independent. The total number of trials is going to be n, and the probability that the result of a trial will fall into category I is the same probability p sub I for each trial. Okay. Now, let's look at what the distribution is going to be for the test statistic. So we're going to first consider the case where there are only two categories, k equals 2. Then P1 plus P2 is going to equal 1, and O1 plus O2 is going to equal n. So the total number of observations is n. Well, if we only have two categories, then instead of a multinomial distribution, we have that O1 follows a binomial distribution with parameters n, the total, and then a probability of being in the first group, P1. Then O2 we can think of as just being n minus O1. And then P2, the probability being in the second category, we can think of as just being 1 minus P1. So let's look at what our chi-square statistic looks like. So we're going to take the sum of O sub I minus E sub I squared over E sub I. Well, in this case, we're really only going to have two categories. So we're going to take our observed minus the expected frequencies, which is NP1. We're going to square that, and then we're going to divide by NP1. And then for the second one, we would have O2 minus NP2 squared divided by NP2. And that's going to equal, let's see, O1 minus NP1 squared over NP1. So I'm not going to change that one. But in the second one, I'm going to substitute in what I have for O2. So O2 becomes N minus O1. We're going to square, N minus O1. And then minus N times 1 minus P1, because P2 is 1 minus P1. So we're going to square that. And then on the bottom, we're going to get N times 1 minus P1. Okay. So let's see if we can clean that up a little bit. So the first term still stays the same, O1 minus NP1 squared over NP1 plus, and then what you should see is that these two n's cancel. We have an n there, and then that would cancel with the n there. So what I'm left with is actually NP1 minus O1 squared over n times 1 minus P1. And I hope you can see that the numerator is actually the same for both of these fractions because we're squaring the numerator. Okay, so what I'm going to do is I'm going to add these two fractions together. So that means that I need a common denominator. That common denominator is going to be n times p1 times 1 minus p1. And then so I'll need a 1 minus p1 for the first term times my O1 minus np1 squared. And then I'll need a p1 for the second term, and that's going to be np1 minus O1 squared. Again, I notice that the O1 minus np1 squared is equal to the np1 minus O1 squared. That means I'm subtracting a p1 and I'm adding a p1 times the same thing, so that goes away. And now I'm going to have an O1 minus np1 squared divided by np1 times 1 minus p1. What I'm going to do is I'm going to write that as all a square. So this is going to be O1 minus np1 divided by the square root of n p1 times 1 minus p1, and I'm going to square that. And then I'm going to divide the numerator and the denominator by n. When I do that, then O1, the number of observations divided by n, is p1 hat. And then np1 divided by n is just p1. And then when I divide, I'm going to take the square root, and that's going to become p1 times 1 minus p1 over n. That whole thing squared. So dividing the numerator and the denominator by n gives me, well, wait a minute, p1 hat minus p1 divided by what looks like the standard error of p1 hat. That's actually going to have a normal distribution. It's approximately normally distributed. Of course, that z is getting squared. Okay, so what's inside the parentheses we've seen before. That's how we compared population proportions. Okay, so that becomes z squared. And we know that if you take a normal and you square it, right, that's going to have a chi-square distribution with degrees of freedom 1. Okay, so we now have for two categories that this has a chi-square distribution and the degrees of freedom is 1. One way to think about that is the degrees of freedom is 2, the number of categories, minus 1, which is 1. This expresses the idea that O2, the number of observations, depends on O1 if we have a total number of observations n, or you can think of P2, the probability of being in the second group, depends on the first group. So then the number of degrees of freedom here is 1, because if we determine the number of individuals or the probability of being in the first group, then that gives us the number of individuals or the probability of being in the second group. Okay, for a general number of categories, we can use some of the same analysis, and that will actually show that the chi-squared statistic, of course, has a chi-square distribution, and the number of degrees of freedom is k minus 1. Okay, so the intuition here is that the sum of the probabilities is 1, or the sum of the observations is n. So the last variable, the last probability, is defined by the others. So if we have k total categories, we really only have k minus 1 degrees of freedom because the last category is going to be defined by the others. In this case, the rejection region for our chi-squared statistic is going to be, we're looking for the chi-squareds greater than chi-squared sub alpha. Okay, and I want you to notice here that the rejection region is always one-sided. Okay, so we've now shown that our test statistic has a chi-square distribution with degrees of freedom k minus 1, and we have our rejection region, so we can now move back to our example. So to complete our example, we need to find the expected values for each of the blood types. So the expected value or the expected number of observations for the A blood type is going to be 41% times 200. That's going to be 82. Okay, for the B blood type, that's going to be 10% times 200. So that's going to be 20. For the AB blood type, that's going to be 4% times 200, and that's going to equal 8. And then for the O blood type, that's going to become 45% of the population times 200, or 90 people. And now we want to do our chi-squared statistic. That's going to be the sum from k equals 1. I think I used an I actually. I equals 1 to 4 of O sub I minus E sub I squared over E sub I. And in this case, we had 89 observations of blood type A. 82 were expected. We're going to square that and divide by 82. And then for type B blood, we had 18 observations, but 20 were expected, and we're going to divide that by 20. Then for type AB blood, we ended up having 12 observations. 8 were expected, so we square that and divide by 8. And then finally for O blood, we had 81 observations. 90 were expected. We're going to square that and divide by 90. Our total, when we sum all this up, becomes 3.696. Okay, so remember that chi-squared statistic, 3.696, because now we got to figure out what our rejection region is. Our rejection region is going to be chi-squared greater than chi for 5%, okay? And so we need to look at what is the chi-squared value for 5%. So I'm going to go to my chart, and the 5% chi-squared value for 3 degrees of freedom is going to be 7.81. So the degrees of freedom is 3 because the number of categories was 4. Okay, and I want you to notice that we had a chi-squared statistic of 3.696. It would be over here on our chart, so we can see that our p-value would be bigger than 0.1. Okay, so our rejection region is that the chi-squared needed to be bigger than 7.81. That did not occur. Our p-value was bigger than 0.1 in this case. In fact, if you run the test using R, you can see that the p-value is 0.296. So in this case, we fail to reject the null hypothesis. So in this case, there is not sufficient evidence to conclude that the proportions of blood types are different than the historical ones. Okay, so you'll see that nowhere did we actually estimate the proportions. Okay, so this is a non-parametric test. We did not try to estimate the parameters, the proportions, okay? But we used this chi-square method. We saw that the chi-square statistic has a chi-square distribution, and so we were able to define a rejection region, and then we were able to say that we could not reject the null hypothesis. So there's not enough evidence to conclude that the proportions are different than the historical ones.